Bismillah ar-Rahman ar-Rahim. Let's start this lecture for chapter number 3, chemistry. Of course, chemistry is an important environmental topic, whether it's environmental engineering or environmental science. It's important once we design treatment process. And after we design it, once we operate, we have to know chemistry. Because everything will depend on what? Fundamental chemical process. Also, if you want to know the fate of the chemical released into the environment, you need to understand chemistry. You need to understand the chemistry. Let's say if we have like a lake, and this lake has, let's say, water, and with this water there's like an addition of benzene. You need to know exactly how much will volatilized, how much will be reacted inside the water, and how much will be settled, and how much will be uptake by the fish. So the chemical process and the fate of the chemical release into the environment are related. Also, it is important to study chemistry because you are predicting how the chemical moves through the environment, either through air to the air, or bioaccumulate to fish, or settling, or biologically degraded, or chemically reacted. Okay? The difference between activity and concentrations, we have to go through it because activity sometimes can be thought of as an effective or apparent concentration. And also, you could see that there is a great difference that include, if you're dealing with seawater, briny groundwater, which means that salty groundwater like brackish water, recycled streams, and highly concentrated waste streams. You could see the change on the activity. You could see that activity now will become different than concentration. And of course, concentration can be typically designated by this, and activity can be designated by this. Okay? Ionic strength is the first parameter that we're going to be investigating here. That this is the equation to find the ionic strength. This is the molar concentration of ionic species in solution, and this is the charge of the ion. If you have like fresh water with no pollutant inside, there is no high salt, so the fresh water, the ionic strength would be from 0.001 to 0.01 mole per liter. And if you go to the seawater, because the seawater has a lot of ionic strength, has a lot of ions, okay, the concentration of the ionic strength become 0.7. Look at the difference. It's because of the salt. So if you have more salts, the ionic strength would be much, much bigger. Now, there is equations that correlate between TDS, total dissolved solids, and the ionic strength. And this is one of the equations that we're going to use. Also, there is a correlation between specific conductance and ionic strength. And of course, these are constants. The specific conductance is in micro MHOs per centimeter. And of course, we measure this using a conductivity meter. This is one way of putting the first equation, where mu is the ionic strength in mole per liter, and TDS is total dissolved solids in milligram per liter. And of course, this is the other equation that we're going to be using. The specific conductance is in micro MHO per centimeter, and you do this using the conductivity meter. And this is an example. There's a probe, and this probe, they put it inside the beaker that has the solution, and you could find out the ionic strength using this conductivity meter. The ionic strength, of course, there is a highly variable in numbers, and we measure, for example, if you look at this, the TDS is part per million. If you go from 0 to 50 ionic strength, this is which is ideal for drinking water, and of course this is using RO, reverse osmosis, and also using deionization, okay, and microfiltration and distillation. All of these will help remove a lot of salt, okay, and will reduce the ionic strength to make it between 0 and 50, which is appropriate for drinking water. Once the salt increase, for example, if it goes from 50 to almost 170, now we could start seeing some more salt. Now we could see some more stronger ionic strength. If you have carbon filter, this carbon filter will make sure that the ionic strength will not go above 170 ppm. If you have like an aquifer, a mountain spring, or an aquifer, you would see the salt of the rocks dissolving in the water and producing a little bit of high ionic strength to 170. And of course, 170, we could call the water a hard water. If you go from 200 to almost all the way to 250, you will see it's still acceptable. But the tap water will go from almost 170 all the way to 350. This is the average tap water, although it's acceptable to drink, but the best is to drink it from 0 to 50 to have enough acceptable ionic strength. Of course, if you go from here to here, this is high TDS water from tap or mineral springs. If you go to more than 500 TDS, you would expect that this is the US, United States Environmental Protection Agency maximum contaminant level. So they consider more than 500 ppm TDS, that is maximum contaminant level. Okay? So the approximation of the activity coefficient when you deal with activity and concentration. I'll give you some examples that if you differentiate between electrolytes, that's what's make your blood moves around. Look at this electrolytes. Lead, sulfate, and bicarbonate. Look at the charges. Non-electrolytes are also needed by humans, but they are not the thing that moves the stuffs around. This is not the things that will make the blood go around into your system. And even in any other aqueous system in the environment. This is non-electrolytes, oxygen, benzene, and glucose. Okay, so what makes these things electrolytes is the charge. Okay, there's an approximation of the activity coefficient that we'll be talking now about and how to solve it. Let's look at this problem so you can see exactly how to use the equation that we just did before. You are studying the visibility of using a reverse osmosis. Now, let's say this is the tap water in the kitchen, and we have a machine, an RO machine, that goes to, after that, cooking and drinking and other cleaning stuff. You are using an RO, okay, system to desalinate. Desalinate means taking salt out of the water. D means taking something out, okay? Seawater, TDS, this is normally acceptable TDS for seawater, ocean water, and inland brackish groundwater. either a little bit of salt, it's not even a little bit, it's medium salt with high salt. TDS typically from 1,000 to 10,000 milligram per liter. He needs to estimate the ionic strength of the seawater and the brackish water. So find the ionic strength. Of course, we're going to use the equation to do that. The ionic strength is, this is the ionic strength, is equal to 2.5 10 to the minus 5. He give you what? What did he give you here? He give you TDS. So you're going to use the equation with TDS. So the seawater, 2.5 10 to the minus 5 times TDS of seawater, 35,000. That is 0.0888. Well, this is, I need to check this because there is something, I think 35,000 times 2.5. Oh, this is wrong. So 35,000 times 2.5. Okay, so this is 0.875 molarity, mole per liter. This is the ionic strength of seawater. Now, let's find the ionic strength of brackish water, a lower limit. Remember, he gave you 1,000 and he gave you 10,000. So, if you multiply 2.5 10 to the minus 5 times 1,000, you would get 0.025. Okay? If you get the other one, 10,000, the upper limit, 10,000 times 2.5 10 to the minus 5, you will get 0.25. So now there is a range, okay, for the brackish water. And there is a concentration of ionic strength for the seawater. Let's look at the second part of the question. This is the ionic strength. Now we found the ionic strength for the seawater and the brackish water. Now, a conductivity meter provides a reading of 7,800 micro MHO per centimeter. When placed in one of these water samples, you have 3 water samples. 1, 2, and 3. When placed in one of these water samples, which water source is the sample from? So you measure it, and now we don't have the numbers. We're confused which one is brackish, which one is seawater, and the reading gives you 7,800 micro MHO per centimeter. Which one of these is this? Is it seawater? Is it brackish water? We'll see. Now we're going to use the conductivity meter. The conductivity, specific conductance, we use this ionic strength times specific conductance. And he gave you 7,800. So, of course, the constant is different for the specific conductance. So, you multiply this times this, you would get 0.125 molarity, mole per liter. Now, 0.125 is between these two numbers. So, it is not close to seawater. So, we are for sure, we are confident that this sample that we sampled now is brackish water and not seawater. Okay? Of course, we use chemical equilibrium and the reactions between chemical A with B to produce chemical C and chemical D, or sometimes you'll have a reverse reaction, so either forward or reverse reactions. I'll try to go through the most important slides in this lecture. And we know the pH goes from 0 to 14. pH 7 is natural. If pH goes above than 7, it is basic solutions. If pH go below than 7, it's acidic solution. And neutral, it's at pH equal to 7. And of course, the equation which shows that this is the hydrogen ion, minus log of the hydrogen ion will give you pH. Okay? And also, to understand the definitions of acid and bases, we should know that the difference between strong acid and weak acid. Okay, a strong tendency to dissociate. Okay, the dissociation, the strong tendency to dissociate, which means that the reaction equation goes for the right. You can see it. If this is a chemical and this chemical has a hydrogen ion, if the reaction strongly will dissociate this and to the right, we can see that this chemical is a strong acid. While if it has less of a tendency, if it's not dissociating, as not going to the right, okay, and there is a tendency, a less tendency to dissociate, we call this weak acid. And how could you mimic, or how could you depict the acid dissociation strength? Is by doing this constant, which is the equilibrium constant for the reaction when the acid is added to the water. Remember the equation we just had before? HA, any chemical with the hydrogen, producing H plus and A minus. Of course, the dissociation constant is H plus times A minus over HA. H plus times A minus over HA. Okay, I think it is good to look at the table that we're going to be showing you in a few seconds. And we should know by heart as an environmental engineer that there is 4 very strong acids: HCl, HNO3, H2SO4, and HClO4. If the HCl added to the water, the hydrogen will be lost. Now you will have Cl minus, and we could call this Cl minus a conjugate base. Same thing if the HNO3, which is a very strong acid, if it loses the hydrogen, you will have NO3 minus, which is a conjugate base. Same thing for the H2SO4. If it loses the 2 hydrogen, you will have SO4 2 minus and ClO4 minus. Okay? Which means that this is a conjugate base, not a strong acid anymore. So the acid, it can lose or donate a proton. Proton means, example, a hydrogen ion. Okay? It can lose it. Look at this hydrogen. It will be lost. Or it is so generous to give hydrogen ion. It will donate. So you can see it. The A minus and the hydrogen ion is free for anyone to take. This is the acid. It can lose or donate. The base, it can gain or accept a proton. Okay? If you have an acid, let's see, this is I mean a base in water, you can see it will be looking for a hydrogen. It will gain, it will accept. So you can see the B minus will be BH. So now we can see that this is a base. So of course we know that if pH is equal minus log hydrogen, the hydrogen is 10 to the power minus pH. Okay, and that's the hydrogen should be in mole per liter. We'll go through this acid-base chemistry. We did discuss this in class, the relationship between H2S, HS, and S minus 2. You can see also that the Kw and the pH and the temperature is greatly affected. So temperature could change on the pH of the natural water and also in the Kw. You can see from 0 to 30 Celsius, you can see the difference between 0.12 to 1.47 in Kw. Same thing for pH, 7.47, and then it will become more, little bit acidic. It's not more acidic, but it's little bit acidic. Okay, so we should know that if H equal to OH is natural, acidic if hydrogen is more than OH, and if the basic solution hydrogen is less than OH, and the equation of course Kw is equal H plus times OH minus, and of course Kw has to be at 25 Celsius for water, 10 to the minus 14. So we know Ka, the dissociation constant. If we have a very strong acid, everything will dissociate. So everything here will dissociate and everything gonna go to the right. And HA, aqueous, will disappear because everything will dissociate and go to the right. So HA, aqueous is equal to 0 for only strong acids. Same thing for a weak base. You can see that this reaction will not proceed, but Kb would be equal to BH, OH over B minus. But for a strong base, this reaction will proceed to the right, and the whole thing will be completely removed. And P minus aqueous is equal to 0. BKA is equal minus log Ka, and BKB is minus log Kb. The only thing that I want you to know is, smaller the value of pKa, the stronger the acid. So if I give you acid A, let's say A, and acid B, and I give you log, or if I give you log, or let me see, if I give you pKa, okay, which is the minus log Ka, and if I give you this is 2 and this is 5, which one of these is a strong acid? Of course, acid A is stronger than acid B because the pKa is lower than the acid B. So that's why acid A is stronger. Whether you have pKa or whether you have Ka. Okay? Now, the same approach will apply to the BKB. So the stronger the base is the smaller the BKB. Okay? Now, in this table, you can see exactly where is the stronger acid. Let's see. HCl is a very strong acid, and pKa is minus 3. Sulfuric acid, H2SO4, is a very strong acid, minus 3. You go all the way down. Now we're going to go to weak acid. Look, it's going to be in the plus now, 1.9. This is pKa. And then phosphoric acid, 2.1. And you can see you could go all the way to the weakest acid, HbO4 to minus 12.3. A very weak acid is ammonia. Of course, the pKa is 23. Look at the variation of the pKa's. The minus 3 pKa, very strong acid. The pKa of 23 is a very weak acid. While the BKB, let's see the chloride ion. Of course, here, once you have HCl, you put it in water, it will lose the hydrogen. It will become chloride ion, Cl minus. The BKB is 17. Now, it was strong acid. It lost the hydrogen. It become what? Chloride ion. Now, this is a very weak base. Same thing here, H2SO4. It's losing a hydrogen in water. Now, it becomes SCO4 minus. The BKB is 17. This is a very weak base. If you go all the way down to weak bases, this is very weak bases. If you go to weak bases from sulfate ion into phosphate, that's 1.7. Now, this is becoming more stronger of a base until you come to the strongest base for our studying. It's amide, NH2 minus. Of course, NH3, the ammonia, losing one hydrogen, NH2 minus, and that's amide. That's a very strong base. Okay? So this is a very nice example that will explain a little bit of what are we studying here. What percentage of total ammonia? Of course, when we say percentage of total ammonia, that is NH3 and NH4 plus. Okay, that is present as NH3 at pH 7. Of course. So now, if we have NH4 plus, it will dissociate to what? You can see in water, the hydrogen here will be lost. So you'll have one hydrogen plus NH3. If you add this to this, you will get this. But in water, NH4 plus will dissociate to hydrogen and NH3. So the Ka is by multiplying concentration of hydrogen times NH3 over NH4 plus. He gives you the pKa of NH4 plus, so now we could use it here. As we said before, this is pKa. Ka is 10 to the power minus 9.3. So he wants to know the percentage of total ammonia, that is this, NH3 and NH4 plus, because this is the total ammonia, okay? And he wants the percentage of this as NH3. So once we found this, we just leave this equation for a while until we find out the percentage of this out of the total. Okay? So we put it like this. NH3 divided by the total ammonia, NH4 plus and NH3 times 100 to find out the percentage. So now we have this equation and we have this equation. Here the hydrogen, we know. The pH is 7. So to make it hydrogen is equal 10 to the minus 7. So we put the hydrogen here. So we put it here 10 to the minus 7, NH3, NH4 plus, and 10 to the power minus 9.3. So for this, you have to make the abbreviation NH3 over NH4 equal 10 to the power 9.3 over 10 to the power minus 7. So this would become equal to 10 to the power minus 2.3. So if you do this, let's do it here. I want to check if this answer is correct. To the power okay, this would give you 200. So NH3 over NH4 plus is equal to 200, and NH4 plus well, we can check it again. I think there's something 110. I think it is 10 to the power okay, so there is a mistake here. It's 1 over 200. Okay, so this is equal to 1 over 200. So now you could redo the equation to be equal like this. NH4 is equal to 200 times NH3. So now the equation, we leave NH3, and we change this as 200 NH3, 200 NH3 times 100. So now this will cancel with this and with this. You'll end up with 1 over 201 times 100, and that would give you 0.5%. So NH3 is 0.5% of total ammonia. Everything is in the NH4, which is like 99.5% is in NH4. Okay, because at this pH, almost all the NH3, NH4 plus total ammonia in the system exists as NH4 plus, 99.5%. We call this ammonium ions. Okay, so we'll try to also state that NH3 is the most toxic to aquatic life. Very toxic to aquatic life. It is toxic to several fish species at a concentration above 0.2 milligram per liter. Okay, so we will be talking about a buffer solution, which is the meaning of capable of withstanding the additions of strong acid and bases with little change in pH. Of course, buffer always is combination of weak acid and their salts, combination of sodium bicarbonate, sodium carbonate, and to form a buffer solution. Well, in buffers, there's two functions: salts, the acids. Example: sodium carbonate, it's to absorb any new acids, and the acids, sodium bicarbonate, is to absorb any new base, hydroxide ions that may be added. Now, we'll just go through this because we have to, and of course the system here, the bicarbonate HCO3 minus can act as either an acid or base and act like a buffer in the ocean. And of course, the job of this bicarbonate is to resist changes in the pH. Remember that if we have a lake or if we have an ocean, the CO2 in the air will be deposited with the rain to the ocean, and it will change the pH. Well, the bicarbonate into the ocean, which is considered as a buffer, will resist this change. Now we come to a very important topic: water hardness. What is the hardness? The most abundant is this divalent cations, calcium and magnesium, the +2 and the +2. It has to be di. Di means two. Divalent cations. It has to be di and plus. So these are the most abundant. These will contribute to high hardness. And the less abundant, Fe2 plus, Mn2 plus, and Sr2 plus. Of course, the classification of the hardness of the water, whether you use this units, milli equivalent per liter, or you use milligram per liter as CaCO3. Soft is less than 50 milligram per liter as CaCO3, or moderately hard from 50 to 150. Hard is from 150 to 300, and very hard is more than 300. And since we talked about water hardness, we should separate this hardness into two: carbonate hardness, CH, which is the presence of HCO3 and CO3 minus and ions. Like if you have calcium with bicarbonate, 2 moles of bicarbonate to produce calcium carbonate and CO2 and H2O. You can see the deposits is from this carbonate hardness in pipelines. Non-carbonate hardness in CH is all other anions. Okay? So the calculation now. Remember from the previous lectures, the total hardness is equal to, of course, the total hardness is milligram per liter as CaCO3, is equal to the concentration in milligram per liter of divalent cations times 50. This is to convert to milligram per liter as CaCO3 divided by what is the equivalent weight of that cations. And we did this in the previous lectures. Now we should calculate also we should know how to find the carbonate hardness, which is to add SCO3 minus and CO3 minus, of course as milligram per liter as CaCO3. And non-carbonate hardness is the difference between total hardness minus carbonate hardness, because this are found in the same water. It will balance. There is some classification of carbonate hardness and total hardness. If they are less than that, which means that both carbonate and non-carbonate hardness exist, which means that this equation is valid. If carbonate hardness and total hardness are equal, which means that only carbonate hardness exists, not bicarbonate, and not both. So NCH is 0 and TH is equal to CH, and if CH is higher than TH, then only carbonate hardness exists. NCH is equal to 0 and carbonate hardness is equal to total hardness. We also discussed the acidity and alkalinity, and I'll stop at this slide. The acidity is defined as the capacity to neutralize a strong base, and is calculated like this. Adding up SCO3, 2 of H2CO3 minus OH plus H. Alkalinity is defined as the capacity to neutralize a strong base, a strong acid, sorry. So acidity is to neutralize a strong base. Alkalinity is to neutralize a strong acid. Alkalinity in mole per liter is equal to SCO3. Look at the difference, 2 CO3 2 minus, not 2 H2CO3. Look at the hydrogens, it's all gone. Here there is a minus OH, here there is a plus OH, and of course plus H and minus H here for alkalinity. Okay? And of course in table 3.6 in the book you can see the difference between alkalinity and buffer capacity, and that's what we did in the previous lectures. So we'll stop at this point.